All right, so now we're going to talk about relationships between the equilibrium constant and the chemical equation. So the equilibrium constant, remember, is products over reactants all raised to their coefficients. So the first relationship, these are similar to the relationships we learned way back in thermochemistry about, flipping the reaction and all that sort of stuff. In this, if you reverse the equation, you invert the equilibrium constant. And that should make sense because if it's products over reactants, in the top case, you would have C cubed over A times B squared. But in this one, on the bottom one, products over reactants would be A times B squared over C cubed, because it's products over reactants. So remember, if you reverse the equation, you invert the equilibrium constant. Number two, if you multiply the coefficients in their equation by a factor, raise the equilibrium constant to the same factor, okay? So if you multiply, so the original equation would be C cubed over A times B squared. Well, let's say that we multiply the whole thing by 2, okay? So we multiply by 2. That means now C is raised to the 6th power, A is squared, and B is to the 4th, right? So you're raising the equilibrium constant to the same factor. So here, see, you doubled the, sorry, I'm like totally spacing out right now. You doubled the reaction and you doubled the exponent. So you're raising it to that factor. A, you raise it to the 2nd power. 2, you're doubling that exponent. So whatever K is, raise it to the same factor. So in this case, if we got K over here, this one would be K squared. All right, sorry about that. On the number 3, if you add 2 or more chemical equations, multiply the equilibrium constants by each other to obtain the overall equilibrium constant. So in this one, the top equation is B squared over A. The bottom equation is C cubed over B squared. Now notice, if we were to do one for the overall equation, these would cancel out, and you'd end up with C cubed over A. Well, look what happens when you multiply these two. The B's cancel, and then you're left with this. So that's what it's saying. Multiply the equilibrium constants, and you will obtain the overall one. I'm not going to go ahead and go through these for the sake of time, but in this case, you are reversing it, okay? So you would flip it, okay, invert it, and you are also dividing the whole thing by 2, or multiplying by 1/2, so you'd raise it to that power. All right, we'll do these in class. You can practice them and go back to it. Expressing the equilibrium constant in terms of pressure. Remember what I said, they'll throw in pressure to try to confuse you. Just pretend like pressure is concentration. So if they give you a problem and it's in terms of pressure instead of concentration, the equilibrium constant in terms of pressure would be the partial pressure of the products raised to their coefficients over the partial pressure of the reactants raised to their coefficients. So don't worry about that too much. The only problem is that the equilibrium constant with respect to pressure and concentration are actually going to be different values because they're measuring different things. So this right here, this equation, using Pivnert, and we can talk about how to get that if you want later, but this would allow you to switch between the two. I do not foresee this happening on the AP exam, but this is the equation you would use to do that. For delta N, that's the change in the number of moles. So it's the total product moles minus the total reactant moles. And R is the gas constant, of course. All right. So there's a practice. We'll do that in class. Units. What are units for Kc and Kp? Well, the awesome thing is there are no units. It's a ratio. So you have molarity on top, molarity on bottom, all the molarities cancel. Pressure on top, pressure on bottom, the pressure units cancel. So it's just a ratio. It's just going to be a number, which I'm sure many of you are happy about. Reaction involving solids and liquids. Sometimes, well actually a lot of times, reactions have pure solids and pure liquids in them. You can't find the concentration of pure solids and pure liquids, so you're actually going to exclude them from the equation for your K value. So, in this case, up here, you have two gases and one solid. Well, the solid can't be included, so we just do the carbon dioxide over the carbon monoxide. On this one down here, this is a pure liquid, so you don't include it, and you would have H plus times HCO3 minus over CO2. All right. I think that's where we're going to stop for now. So, see you next time, I guess.